Greetings, cultivators from around the world. Jordan River here with more GrowCast podcast, wondering if that seed is a male or a female. Today we have Nick from Rooted Leaf. Now, if you're a member of the Order of Cultivation, you've seen this guy on the streams before, and he is a wealth of knowledge. Really, really smart guy. He's going to talk about carbon-forward nutrition. He's going to talk about terpenes. He's going to talk about fertilization and hash making. Very good episode. Let me know what you guys think as always. Before we get into it with Nick, though, shout out to Rimrock Analytical, rimrockanalytical.com. Code GrowCast for free shipping. And don't forget code BULK10 for the pricing discount. That's right, BULK10, I believe, gets you 10% off anytime you buy 10 tests or more, lowering that price to about $11.50 per test. Super, super affordable, so you don't waste any time feeding or growing these plants in any sort of medium. Rimrockanalytical.com will tell you if your plants are male or female right after they come out of the ground. As soon as you have the true leaves, you just snip off the cotyledons and you mail them off, and they'll tell you who's male and who's female right there, baby. And I will tell you, I just got my Rimrock tests back at 10:15 on a Saturday night, I believe it was. These guys work around the clock. I've seen members get tests back on Sunday. It's the fastest, most reliable sex testing that I've ever seen. Again, rimrockanalytical.com. Code GrowCast for free shipping. Code BULK10 for orders over 10 tests. And stop wasting time sexing your plants when you can knock them out. Now, unfortunately, my 2 Molokai Frost were male, but I was glad to find that out instead of waiting all that time and then being disappointed. Now I'm already moving on with my life. Trust me. Go to rimrockanalytical.com and grab some sex tests. Code GrowCast always and BULK10 for 10 or more. All right, thank you for tuning in, everybody, and enjoy the program with Nick. Hello, podcast listeners. You are now listening to GrowCast. I'm your host, Jordan River, and I want to thank you for tuning in again today. Before we get started, as always, I urge you share GrowCast with a grower, turn someone on to growing, of course, and check out the Order of Cultivation, our secret society of growers. Here to lift each other up. Don't join if you're just going to cause beef. We don't do that around there. Welcome to the show, everybody. Very excited to have first-time GrowCast guest, but the members at the Order have already met this guy. I bumped into him at a Jinx Proof meetup down in Oklahoma. It was just an incredible appearance. He hopped on GrowCast TV for the live stream, and he stayed for a little while because he knows a lot of stuff about cultivation. This is going to be a really powerful episode, and I'm very excited to introduce from Rooted Leaf, the nutrient company, we have Nick on the line. What's up, Nick?
Hey, Jordan. Hey, everyone.
Welcome, man. Thank you for coming on the show.
Thanks for having me. It's a pleasure to be here, and definitely looking forward to the topic today.
Fuck yes, man. You are a wealth of knowledge. I loved your last appearance. Before we dive into all of the cool shit that I want to talk about, can you first give a little bit of background on yourself, and then more importantly, Rooted Leaf? What caused you to create Rooted Leaf, and what your mission is for Rooted Leaf?
Yeah, so me personally, I have a background in chemistry that is pretty expansive. It spans fermentation chemistry initially, because in my early 20s, I had this idea of starting a kombucha brewery. And one of the things I started to experiment with was, different steps in the fermentation process using different substrates, and finding that the results on the back end post-fermentation were drastically different. And so this kind of inspired me to look a little bit more closely at ingredients that people would otherwise assume are just interchangeable, but in reality, they have a big impact on the final product on the back end. So that kind of carried me forward for a couple of years through fermentation chemistry. And then I got involved with a little bit more industrial chemistry. So I was doing things like manufacturing surfactants, and I was formulating degreasing compounds, used at truck washes and car washes and things like that. So I had a good understanding of, chelation chemistry, surfactant chemistry. I kind of got into the nitty-gritty details, even looking at three-dimensional structures of the actual surfactant molecules, the individual micelles that are made. And all of this stuff is very important. Just as like one quick example, if you want to create a type of spray to apply like a cleaning solution, it makes sense to pay attention to how homogeneous are those little air bubbles, because everybody likes the soaps and the suds, but the actual shape is very important. And so if you do it right, you can create something that, whose chemical properties also kind of dovetail in with the physical side of cleaning things, scrubbing, for example, using high pressure hoses to wash stuff off. So it gets really, really nuanced, and in these little cracks and crevices of industrial chemistry, I think most people just don't pay attention to it nearly as much as I did. I was, thinking this was all cool stuff. And then back in about 2014, 2015, Washington State legalized cannabis for recreational purposes. And so with the introduction of the recreational market, I figured I would start looking more seriously at cannabis nutrition in a professional sense. I've been, involved in the cannabis industry since about 2008, 2009. And I've always had a passion and an interest in this plant because it's something that, for a lot of reasons, is so fascinating. But for me personally, it's always been an inspirational thing to look at, just in terms of, the culture and the economy, even the chemistry and the biochemistry of cannabis plants. Such a unique plant for so many different reasons. And so I started to think more critically about ways to better optimize, the productivity of these plants in order to get more terpenes, more cannabinoids. And that kind of led to a spot where, in April of 2019-ish, we opened up a manufacturing plant with some technology that we had developed and some products that were kind of put together based on the understanding that cannabis plants operate in a very, very specific and nuanced way, much like these, as I mentioned earlier, the bubbles and surfactants. The particular shape and size is very important too. So it's not enough to just say, it's a soap and that's it. And it's not enough to say, it's a fertilizer and that's it. There's very, very nuanced details about how plants actually process nutrients that, to me, just wasn't being addressed in the market, particularly for a high value crop like cannabis. It seems like there's a lot of research and development that can be done in the sector of high value goods because, a lot of the farmers can kind of afford to play around with the latest and greatest technologies, and they have the ability baked into their business model to fine tune things that set them apart from their competitors. And for me, that was always, nutrients being one of the more important things. You are what you eat, you reap what you sow. Definitely what you put into your plants makes a big, big, big difference as far as the overall expression of possible outcomes. And, for the past 3 years, that's kind of been our focus. Our bread and butter, by and large, has been to try to better understand what it is we're doing. And through conversations like this, it's a matter of removing our own ignorance and lack of understanding and gaining clarity on what it is that we see happening with these plants.
Absolutely, man. I couldn't have said it better myself, too. There's so much opportunity to learn because of all the money that's in this industry. That's why I've said that on this show time and time again, which is with the cash crop, hopefully we're going to learn all sorts of new things about agriculture in general and chemistry in general and all this stuff. So I'm very, very excited to dig in. I would like to kind of cue you up for this. You talk about, how you wanted to address the cannabis-specific needs and specifically aiming to produce more terpenes and cannabinoids and all those, flavonoids and all the goodies in there that we like in that trichome head. And I know that has a lot to do with carbon delivery. Now, we are in Nug Mashing May. We are talking about hash all month long. And man, that's what these hash makers are after. They're after a nice high level of usually a wide variety of terpenes. And it seems to me like when you make sure that you're getting that carbon in there, whether you're supplementing in many different ways, which we'll get into, or humic acids or all this stuff, seems like carbon plays a big role in trichome farming. Can you talk about that a little bit?
Yeah, definitely. And this is maybe a good introduction for Rooted Leaf Agritech as well. We're pioneering this new field of fertilizers. It used to be that you would have traditional or conventional salt-based fertilizers, and then you would have organic-based fertilizers. And really, there's a new category that's being developed. We're certainly one of the leaders and one of the pioneers, but I think there's a lot of other folks in the same space that are doing good work. And the idea is that it's a carbon-based nutrient or a carbon-based fertilizer. And the reason that's so important is perhaps easiest for the cannabis farmers to understand relative to if you were growing something like tree fruit or strawberries or blueberries. You would still see the benefits of a carbon-based program, but the upside for cannabis farmers is that all of those monoterpenes and sesquiterpenes and even the cannabinoids themselves that accumulate inside of the trichome heads, those are all going to be roughly 80 to 90% carbon by weight. And so this is a very, very mechanical question here. It's a very mechanical operation. If you want more of something that is mostly carbon by weight, you're probably going to need more carbon. And the best way to illustrate that would be to ask people to think, well, if you see a nitrogen deficiency in your plants, your response to correct that nitrogen deficiency is to apply the thing that the plant is missing. as opposed to looking at the plant, realizing it's deficient in nitrogen, and then deciding for whatever reason that you're going to apply phosphorus,
Right.
or you're going to apply potassium or calcium or magnesium. None of those things really fit into the needs of the plant at that point. And similarly enough, for cannabis, it likes to take in a lot of carbon, and it needs to take in a lot of carbon in order to produce high concentrations of terpenes and cannabinoids. These are very high energy compounds that require a lot of energy coming into the system and a lot of availability of the substrate or the building blocks. This is why you have to shine very intense light on cannabis plants to get maximum productivity. It requires high energy and it requires a high carbon load. So historically, the way to supplement the carbon has always been in the form of CO2. And so now we're in this environment, or now we're in this market, nationally even, it's true that most of the models that are built out are closed loop air models, meaning that you seal a flowering space and you shove a bunch of gear in there, like you got your heat pump in the form of lights, and then you have your air conditioner because you need to cool the space. It's a sealed system. But then you're also watering the plants, so you need to dehumidify the space once that water has been transpired. And so we kind of set up this really interesting motor with components that effectively work against themselves, simply in order to maintain the optimum balance for loading carbon into the plants.
Loading them into the air.
Yes,
Right.
yes, specifically in the air. And there's a lot of reasons why CO2 supplementation in the air has its inherent limits. And it's probably not the best way to do it. This is one of those things we'll kind of get into at large in the context of terpene and biosynthesis, or cannabinoid biosynthesis overall. But it's interesting for me watching the model that's been developed, noticing that most growers are feeding nutrients that contain no carbon, and they're expecting their plants to produce more carbon containing substances. And for me, it's always a thermodynamic equilibrium question, is like, where are you getting that carbon from? And if you're not supplementing CO2 in the air, what else are you doing? I've never met a grower, a professional or a hobbyist or a home grower, that sealed up a flowering space only to drop the CO2 concentration,
Right.
or even just to maintain atmospheric concentrations of CO2. They always do this with the specific intent of raising the CO2 concentrations and then keeping the temperature and humidity kind of in check to allow for maximum, transpiration efficiency. People like to kind of look at the VPD like it's the holy grail, even though there's more fudge factor, more plasticity baked in than, you would get if you just simply Googled it. But
So true.
still, the idea is pretty ubiquitous that everyone chose by and large to feed, carbon deplete nutrients into the roots and then shove a bunch of carbon in the form of a fully oxidized gas, a monomer no less, meaning that it just has a single atom of carbon. They just decided to shove that into the air without really paying attention to more specific nuances like, well, how do plants actually take in that CO2? What are they doing with it? How do they process it? How do they maintain, equilibriums in terms of energy coming in and energy going out? These are all things that are kind of still being explored. It's certainly on the cutting edge of, biochemistry and plant physiology. But I think we stumbled onto something, with the carbon-based approach that really allows us to remove what is otherwise a bottleneck in the operation. And as a result of removing that bottleneck, we see massive increases in the concentration of terpenes and cannabinoids overall. And it's simply because we're supplying the building blocks that plants depend on and that would otherwise be bottlenecks. They would be limiting factors. The plants have to spend time. It requires energy going into the system that takes away from the plant's ability to continue down that path. And so if we identify these steps that are rate limiting and we come in and we supplement the substrates, or we somehow remove that bottleneck, it seems like the throughput is significantly higher.
That is very, very interesting. I was able to sample some of your product, very impressed by it. And you can tell that there's just a bit of a difference in there when you load in the carbon. I do really quickly want to make sure that listeners know that Nick did create a code GROWCAST at rootedleaf.com. I wanted to make sure we didn't get too far into this episode before I drop that out there. You can find Nick's work at rootedleaf.com, and code GROWCAST saves you like 20% or something. Thank you for doing that, Nick. That was really cool of you. He totally just volunteered to do that. Very, very cool of him. So yeah, so the idea of, I want to dig in on a couple of things. When you're dealing with the carbon that you're feeding, I see a lot of these products have something like carboxylic acid. Is that what you're using? Is it, can you extrapolate on this idea of one carbon molecule not being enough?
Yeah, and the idea is actually pretty simple and straightforward. If you look at monoterpenes, which are probably a good example for us to talk about because they're pretty low molecular weight, and monoterpenes kind of represent, I guess you could call like the lowest molecular weight dank sauce that people are looking for. within the trichome heads. I've never really heard of people talking about needing isoprene or hemiterpenes. And so we'll just start with monoterpenes, mono meaning one. Kind of the basic idea is that there's 10 carbon atoms and there's 16 hydrogen atoms. And there's two things to point out in the chemical or the molecular formula for monoterpenes. The first is that we're dealing with 10 carbons, whereas in CO2, we're dealing with one carbon.
Uh-huh.
And then the second thing to notice is that the H16 versus the O2, one is fully oxidized, the other is fully reduced. And this is going back to a very, very simple equilibrium that has to be maintained in all of nature. It's the balance between reduced and oxidized states or redox states. The best example I can give to people is if you want to throw yourself off that equilibrium, go ahead and take a really deep breath and hold it. Don't breathe out, because what you're going to start doing is building up the reducing equivalents. And what happens when you exhale and you inhale again is you're taking in more oxygen and you're oxidizing what is being reduced. And so this balance always, always, always occurs. Every breath you take in and every breath you release, your body's maintaining a balance between reduced and oxidized states of metabolism as a way of kind of maintaining equilibrium, the amount of energy coming in versus going out, either passively or actively through metabolic processes. Plants are much the same way. So if they start with CO2, what they're starting is the smallest possible form of carbon that happens to be fully oxidized. Okay, so what we're doing here is scrubbing CO2 out of the air, which is an active process. It's not a passive process. The CO2 has to be converted. This requires chemical energy, and this requires light, obviously. It's all driven by light. So in the process of converting the CO2 into C10H16, there's a couple of things that happen. One is a change in states, being fully oxidized, CO2 kind of useless to the plants. Being fully reduced is very, very useful to the plants.
Okay.
And then there's this, what I call polymerization occurring as well, where you have carbon atoms being joined together. Instead of one carbon in the form of CO2, we need 10 to have one single monoterpene. So now we're asking the plants to effectively, let's just assume that this is a linear equation here for a second. It's a lot more complex than I'm about to make it out to be, but let's just assume that every single CO2 that goes into the plant makes its way into a monoterpene. Well, that means inherently that just to access the carbons, that the plant is going to need to take in 10 molecules of CO2. And then the hydrogen, obviously, the proton pump is generated from the splitting of water. So as plants take water up, they like to split that water. They're really, really, really good at it. And they oxidize oxygen, which is kind of a really crazy and fascinating, infinitely fascinating phenomena. Very nuanced detail about plant biochemistry and physiology. But, the point is they generate that reduction power and they kind of combine that with the carbon to get that reduced carbon species that we like to refer to as monoterpenes. All of this requires energy going into, this work that's being achieved and the work that's being done.
And when you talk about these other delivery methods like humic acids and things like that, they're long chain, more carbon based, or no?
Yeah. And, there's a structural and a functional difference in carbon. It's kind of hard to explain without referring to it as a Pandora's box of possibilities. Because if you really think about it, plants start off with CO2 and they end up making hundreds of thousands of different molecules. The color of lavender buds, the zest of an orange peel, the fibers in artichoke hearts, all of this stuff once upon a time was CO2 in the air. So they take one thing and they make hundreds of thousands, if not millions of different things out of it. And so it's really, really complex to talk about like what is the specific flavor of carbon that plants are looking for. When it comes to classifying carbon based on structural or functional properties, you start to see some differences between things like the longer chain humic substances that really just go into the soil. They do a really good job of contributing to the soil structure, the soil porosity. There's physical and chemical properties that are affected, like water bridging and nutrient chelation, micronutrient chelation in particular. All of this stuff is really, really good, but it's not quite the flavor of carbon that plants are looking for their internal purposes.
Oh, wow.
I think the best way to describe this is to say if you have a high horsepower race car that's producing 1,000 horsepower, 2,000 horsepower, you probably need a very specific octane rating on your fuel. It's not enough to just take a piece of charcoal and put it into your gas can and expect the car to run on that. And even furthermore, even if you had refined gas and it was 87 octane or something like that, your car engine may not run very well on 87 octane.
Right.
If you have a race motor in particular, you're probably going to be looking for something that's 110 octane or higher, just because you need that particular level of refinement to power the amount of energy that's being produced in that particular system. So plants are much the same way. They're not just looking for carbon just because it's carbon. That's way too simple and simplistic of a description. They're looking for very particular, very specific flavors of carbon that happen to have huge amounts of stored energy, and they kind of fit the right shape. It's the right octane rating for them. Every time that they, burn a piece of this carbon fuel, they get a lot of energy out. And it's something that's extremely refined. It's not something that just is passively accepting, large amounts of substrates. In other words, the specificity for these flavors of carbon are very, very tight. They can't accept, lumps of charcoal as the fuel source. They're just not equipped to do that. And so with humic substances being in the soil, they're not really contributing to the primary benefits that we're seeing with our carbon-based nutrients in the same capacity. We're really looking at some of the lower molecular weight organic acids, some of the more primal ones that are like your 110 octane race gas. They're the ones that provide a very, very high value because they have all the right characteristics that the plants are looking for. And as we've kind of identified those over the years, we've started to realize that those are the fuel sources that plants are otherwise limited by, in terms of being able to produce terpenes and cannabinoids. If you just simply give them a little bit of extra fuel to burn, it turns out that they will take that carbon, that specific carbon fuel source, and pump out something that's mostly carbon by weight anyways. So it makes sense from a very simplistic mechanical perspective. It makes sense from a thermodynamic equilibrium perspective. And it also makes sense if you look at test results that we get from, growers that are using our products. It's not uncommon for terpenes on the dry flower to come back in the 5 to 7% range, oftentimes close to 6 to 8%, depending on cultivars and all that good stuff. But, this huge spike that we're seeing in terpenes and cannabinoids is attributable to the fact that we're quite literally delivering the building blocks that the plants are otherwise seeking. And they're seeking it to such an extreme degree that they're taking all of the energy they can possibly get from being, in direct light, very, very high ppfds, very high micromoles of light intensity coming in. They require that to create this high octane fuel source. We've identified that. We've come in, we're dumping it directly we're doing fuel injection basically into the plants.
Okay.
And we're watching as, basically instead of 1,000 to 2,000 horsepower, we're watching these plants make 3,000 horsepower because we can effectively load more carbon than you would get from 3,000 ppms of CO2 in the air. And that's a very, very interesting aspect.
I want to dig in on that. So you said these lower molecular weights. And I don't know if it was you I was speaking to or another guest that was talking about carbon forward nutrition, but they literally described it like the smaller it is, the better the plant takes it up. Like I don't know if that's what you're talking about, like these carboxylic acids, and it passes through the plant and it's more uptakeable. What? Because it's literally smaller? I mean, that seems pretty mechanical, but you tell me though, if I'm mistaken.
Yeah, part of the molecular weight certainly has an effect. Overall, you could look at things like solubility as a function of how big is this molecule, how easy is it going to be to dissolve, and how much can I get dissolved all at once. So the benefit of these organic acids, particularly the low molecular weight ones, is that they do kind of fit in to, primary metabolic pathways, but they're also really soluble, and meaning that they have the ability to be delivered to plants, and then they can act on those really quickly. If you look at things like humic substances, there's a certain molecular weight or a certain length of that carbon chain that eventually is just not going to become soluble. And I think really, really good humic substances are partially characterized by their degree of insolubility, because you want some of that physical structure to be present in the soil. You want some of that carbon to be structural rather than soluble. You want it to contribute to the porosity and the aeration, the water infiltration. You want it to kind of condition the soil in the right way, give a home for fungi and microbes and things of that nature. So yeah, the low molecular weight ones, it's interesting because, as plants grow in the light, there's all of this light energy that's coming in, and the chloroplasts are acting on that light energy. They're taking it in, and they're trying to funnel all of that energy out to a variety of pathways that utilize the energy to do things like reduce nitrates, reduce sulfates, reduce carbon. There's a lot of chemical reduction that kind of goes on.
Jeez.
And so if we can, sort of provide the energy that the plants are looking for naturally, because they would otherwise spend time producing it, and that requires energy coming in from the light. But there's these concentration gradients, these proton gradients that get generated in the presence of the light. And as it happens, most of these low molecular weight organic acids, they're always going across, a variety of different membranes. They're being transported in and out of various organelles within the cells. And their function basically is to create an equilibrium. They're highly available for most, if not all, of the basic plant processes. And so it makes sense that if you could supplement that to the plants, given the ubiquitous nature across not only, every single cell, but within the cell compartments themselves, what you start to find is like, hey, you're contributing to the work that the plants are doing. You're coming in and basically working with them. You're allowing them to harvest energy for free that they otherwise didn't have to spend time and did not require the energy coming in from the light to power that process.
Wow, man. This is a good transition to something you talked about before the show a little bit. I mean, you were talking about myrcene, beta myrcene, and how it kind of rearranges or how it acts under light. Can you talk about that? We'll be right back with Nick from Rooted Leaf. But before that, Plant Revolution, the makers of the Great White line. You know I love Plant Revolution. Jim Egan is a close friend of mine. He's been on this show, and it is a family-run business, you guys. If you like supporting small family-run businesses, this is a great option. Great White makes all the microbes you need from their mycorrhiza and trichoderma blends to their beneficial bacteria. I've been using the crap out of their Orca, which is a mycorrhizal liquid application, and it's got a little bit of beneficial bacteria in there too. Really, really great product to continually get that fungal delivery throughout the growth cycle of your plant. No matter if you're potting up or down or in a seedling stage solo cup, Orca is maybe my favorite product by Plant Success right now. Now, of course, the king crab is a super clean, beneficial bacteria. If you don't have any microbiological products in your garden right now, it's probably the biggest thing you could do to improve your quality with just one simple purchase. Find it at plantrevolution.com. Code GROWCAST is live for, I believe, 15% off. And try out the king crab, try out the Orca, throw in some Myco Chum. You will not go back. I love these guys. And again, small family-owned business. It's really incredible what they're doing over there. And Jim Egan will be back on the show. I ran into him at Canicon. He's such a wonderful guy, and they're doing big things over there at Plant Revolution and Great White. Check it out, plantrevolution.com. Find them in the shelves at their local Hydro store near you, and tell them GrowCast sent you. And use code GrowCast online at their website for savings. Thank you to Plant Success. Let's get back to it with Nick. This is a good transition to something you talked about before the show a little bit. I mean, you were talking about myrcene, beta myrcene, and how it kind of rearranges or how it acts under light. Can you talk about that?
Yeah. And the basic gist is that plants do a lot of work. They spend a lot of energy, takes them time to build up molecules. So they build up carbon from the form of CO2 into monoterpenes. And they include things like organic acids in the mix, certainly with all of the cannabinoids. They are produced by plants in their acidic form. And so what's the first thing that humans do once we harvest the flowers? We dry it out and then we start to cure it. The process of curing is actually better referred to as decarboxylation, meaning that you are removing a carboxylic acid functional group. The essence of our obsession here at Rooted Leaf is how did that organic acid get into the equation in the first place? The plants built this up, put it in, we harvest the flower, we take it out. And so there's the symmetry that's happening here with the plants and their, desire to make these substances and compounds in particular flavors, organic acid forms of these substances. So,
yep. Botany of desire, baby. That's the 11 herbs and spices.
Yep. So when plants produce terpenes and cannabinoids, when we're curing flowers, it's oxidative decarboxylation, meaning that the oxygen that's present in the air is sufficient. That's all that you need basically to effectively cure the flowers, decarboxylate them. The plants will off-gas the CO2. There's something else that happens though, besides with cannabinoids being decarboxylated. There's something that happens with monoterpenes, and monoterpenes like myrcene are really interesting because in the correct circumstances, I'm not going to say this is true in all cases because hash making is definitely an art and a craft above all. This requires basically the process of making hash requires exposure of monoterpenes to light in the presence of oxygen. So what happens when you have oxygen present in and light as well? Well, you start to get reactive oxygen species that can form. Oxygen can kind of capture that electron energy and then it can pass it. And in certain cases, if that energy is too high, you start to break down the monoterpenes, and nobody likes to oxidize all of their monoterpenes out of the flower. So this is why curing happens in a stored environment and with very, very specific conditions. Temperature is a big consideration. Good luck trying to cure your flowers at 85 to 90 degrees Fahrenheit without having all of the monoterpenes off gassed.
Yep.
You may be able to find some clever way to change the actual pressure by creating a vacuum or something like that, or a vacuum chamber, and then curing your flowers. But by and large, in nature, the best way to do it is just to keep it in a cool, dry, dark spot. You don't want too much light, but you want just enough light. So why do you want light in the equation? Well, as it turns out, light provides the energy that myrcene specifically needs to undergo this transformation. And what happens in this transformation is the light that is absorbed by oxygen gets released into this molecular structure of myrcene. And if it's too great, as I mentioned earlier, if that energy is too high, then myrcene is going to off gas. Basically, it's going to oxidize, it's going to break. Those bonds are just not strong enough to hold that kind of energy without breaking the molecule. This is a very unfortunate and tragic circumstance. We don't want this to happen. But in the correct conditions, the light energy and oxygen that get released within the chemical bonds of myrcene allow myrcene to basically get reconfigured and reshaped in three-dimensional space. And there's this new sort of derivative that's created. And there was a paper written about it back in 2014. Some French researchers had basically asked the question, why is it that hash, which is aged and cured and exposed to oxygen and maybe light, it looks a little bit brown relative to the starting material, which may have been lighter in color. So clearly there's been some change in the chemical soup of what's going on there. Well, why is it that hash is significantly stronger than fresh flower? What's going on with these monoterpenes and these cannabinoids? Because there seems to be something that is potentiating. In other words, it's making it stronger. It's making it more than what myrcene does. And what they ultimately found was that myrcene undergoes this light-induced rearrangement into a terpene that they named hashinine. Kind of ironic, not ironic, but very fitting that they called it hashinine. It's a terpene that gets produced primarily during the hash making process as myrcene is exposed to the light in the presence of oxygen, and it's done with care. Obviously, it's a craft and a skill, but this hashinine compound is significantly more potent than myrcene, which kind of explains why good hash, when it's made properly, will definitely pack a serious punch. And it packs a different kind of punch too. The original parent monoterpenes that started off in the material may have completely different effects than some of the derivative terpenes that are produced as a result of making good hash. If you do it properly and it takes, let's say, 6 to 8 months to make this appropriately, you may be left with a product that is significantly more potent. And that's always been kind of a fascinating aspect of, from my own personal perspective, is it's almost like the plants are aware, or they somehow intuitively know, that the compounds they're producing are destined for oxygenation rather than oxidation. And that happens post-harvest, post-curing. So it's a little bit more perhaps esoteric and philosophical, but I almost feel like the plants understand at some level that the compounds they're producing are going to be further acted on by humans, much like humans are, think about humans like enzymes within plant tissue. Enzymes are out there doing work, they're converting this into that, and they're passing energy back and forth. Humans are kind of doing the same thing if you think about it. We're really just harvesting the flowers and then using that. We're changing it in the presence of this to make that, in the context of making hash. Obviously, it's curing, it's aging, it's the proper storage. And this gives rise to more potent versions of compounds that are native to the parent material.
That's really fascinating, man. This idea of light exposure during the dry and cure period, this is something that's become a big no-no here in the modern, like westernized, cannabis scene. When I was down in Jamaica, the guy who hooked us up with the Jamaican bud that we found, actually, I think 2 people told us this. He said they save all the green stuff for the tourists because the tourists don't want the brown shit. But the brown shit is the shit, is what he said. And what they do down there is, I think he said they wait for a cloudy day and they dry it outside. They dry their bud outside. They dry it in the sun. And when I first heard it, it seemed so counterintuitive and just, like you said, kind of volatilizing all. And maybe it is. But now that you've said that there are chemical, reactions taking place after harvest under light, maybe it's not all bad. Maybe if we understand it and we can fine tune it, like you said, we can actually create something new and more powerful. Is that like a fair statement, what I just said?
Yeah. And some of the work that's being done could be enzymatic. I think that there's still enzymes that are active that are kind of, in the
Hanging
process of
around.
reconfiguring. Yeah, they're hanging around. Although, if you really look at it, the majority of the energy that's coming in at that point is definitely coming in from the light, and how that light energy is dispersed across that molecular framework, or all of those individual structures. That's something that's mediated by and large outside of enzymatic activity. I think it just requires oxygen in the presence of light to accept the charge. And then if myrcene, for example, gets close to the oxygen and there's some transfer, and you can oxygenate myrcene effectively without oxidizing it, then you get these oxygenated derivatives of the parent material. And there's hundreds, if not thousands of them that are
Right.
possible. It's not just like the one that's there. And to kind of back up one step too, I should have mentioned this about the pools of organic acids as well. There's not just like one or two flavors of organic acids. There's perhaps hundreds of different derivatives, and they play different roles within the plants. And so if you find the right ones that are really the optimum fuel source, that's where you start to get a massive throughput. And then similarly, in the context of hash making, if you just find the right combination of variables, you find kind of the right fuel source, quote unquote, meaning the correct exposure to light in the presence of oxygen with the correct dehydration percentage. Like, there's so many different things that can be done with only a couple of simple variables to kind of figure out, like, how much light do I need, how dry does this product have to be, and how much oxygen should be present in the equation. These are all very, very interesting and nuanced bits. And I'm always fascinated and surprised by, the hash makers that are out there that are really, really skilled at their craft. They're always finding new ways of guiding plants down this transformative series of transformative pathways.
It's true that you're right. They're like little MacGyvers. Whatever they need to do, those hash makers are on it, man. I know you get to try a lot of different products grown with rooted leaf, especially hanging out in Oklahoma. I know you're all over, but shout out to John, a friend of the show, who was using rooted leaf and hooked me up with some samples that were amazing. Have you got to try rooted leaf hash? I mean, I'm sure that someone's given you some hash made from your product, right?
Yeah.
What do you? Yeah, have you gotten to try that?
Without a doubt. Yeah, it's very intriguing to see what happens, because one of the things that I think we're doing that I don't really see a whole lot of other people doing is supporting and contributing to flavonoid biosynthesis. And I always perceive it as a trifecta with plants. They have cannabinoids, they have terpenes, and they have flavonoids.
Right.
And perhaps the flavonoids aren't as concentrated in the trichome heads. That's where you're more likely to see the monoterpenes.
Well, sometimes, man. Yeah, sometimes you see those purple leaves, but sometimes when you scope those trichome heads, that anthocyanin bleeds right up through the stem stalk and colors it. You're right, though. It doesn't seem to be as... That makes sense when you say it's not as concentrated. That does make sense.
There's a lot of similarities, though, in the pathways, because cannabinoids themselves technically are just children of two. They're like children molecules that are from two distinct parent pathways. The one pathway that everybody's familiar with, we'll just call it the terpene pathway. It's how plants produce terpenes. That's more or less one of the two halves. The second half is the phenylpropanoid pathway. There's a compound called olivetolic acid that's required for the biosynthesis of all cannabinoids. And if you don't have olivetolic acid, there's no substitute for that. You need that ring structure, which comes from the phenylpropanoid pathway. So, being able to support both pathways by loading the substrates into them is very important. It's very effective at getting higher concentrations of cannabinoids. But the same pathway that gives rise to olivetolic acid is actually responsible for giving rise also to things like anthocyanins and pigments, and flavonoids certainly are associated with that. So we're really just dealing with, a class of compounds, like cannabinoids being related to flavonoids. There's a lot of similarities there, and I feel like there's a strong entourage effect as well. But yes, to answer your question, the hash that we've seen grown with rooted leaf fertilizer definitely is significantly different than hash that's not grown with rooted leaf. And I think part of it just comes down to monoterpene expression. It seems like, cultivars grown with rooted leaf get significantly higher concentration of monoterpenes, which a lot of hash makers know that's what dumps. That's what you want. You want a high fraction of monoterpenes.
Ooh.
And we see numbers go through the roof. Like, we had a sour banana sherb come back from Oregon, tested at 2.27% myrcene, just myrcene.
Whoa.
And I think the total concentration of terpenes was 5.9%. So it was split between, half a dozen to a dozen but the major one was Beta Mercy, and that was at 2.27%. So of course we look at something like that and we say that's a really good cultivar that you need to, turn into hash, because it's going to provide you with a high quality product that's going to be significantly more potent and different depending on how it's processed and made, obviously. But yeah, big differences overall.
Oh man, I would imagine. So let me ask you this. My understanding is that these terpenes, they're like a volatile plant alcohol. And please, when I'm done saying this, correct me anywhere I'm wrong. But it's supposed to be this plant alcohol. It's very volatile. When we put it in hash form and then press it, we end up with this rosin. It seems to me like the terpier it is, the more it has this oily sheen, right? Or you take a look at the diamonds in sauce, and all the terps are in this sauce. Why is this alcohol, when it's concentrated and I'm looking at it, look like an oil? Is there any relationship between oil and alcohol there, or is it just the way it appears?
Well, so technically monoterpenes are not alcohols. They don't have a hydroxyl
Oh, is that right?
functional group, but certainly in the speciation of terpenes, you can get some alcohol functional groups, involved in the mix. I think with the esterification reactions, you see this happen. Basically, it's what happens when carboxylic acid meets an alcohol, and the two have a child, basically a child molecule. That's what esters are. And, monoterpenes are hydrocarbons, and so it makes sense why they're a little bit resinous, why they're a little bit
Okay, oily
sticky and greasy.
yeah.
Yeah, they're hydrocarbons. So they're a little bit oily, they're a little bit slick. But certainly, you have some of these oxygenated monoterpenes that start to take on different characteristics. Hash, for example, even if it's really, really strong hash, can actually be fairly dry to the touch.
Yeah, no kidding. Some cultivars are like, you touch those trichomes, they're like grains of salt. Yeah, man, it looks like you nailed it. The hydroxyl presence making some terpenes terpene alcohols. I've been improperly referring to them all as volatile plant alcohols, and I guess I was wrong about that. Thank you for updating me on that, Nick.
And some of them, like linalool, produced in fairly high concentration in plants, that is a terpene alcohol technically, and so it does have that
wow.
hydroxyl functional group. Yeah, so think about it like balance and conservation of energy. If the plants are trying to make monoterpenes, and there's some derivatives of those monoterpenes that they can make by attaching some functional groups like hydroxyl functional groups and making alcohols out of them, it seems to allow plants to dissipate stored forms of energy and accumulate metabolites that are present inside of trichome heads. So part of it just comes down to a balanced charge that the plants have, which can help kind of dictate how the speciation of monoterpene biosynthesis happens. But it's such a complex path. There's so many different factors that go into all of the stuff that it's really, really difficult to just attribute or describe the function of terpene biosynthesis to like one thing or two things or even half a dozen things. I always go back to, the truth that monoterpenes produced by plants often guide interactions across entire kingdoms of life, meaning that you have, plants producing compounds that act on pollinators like bees, they act on humans, they act on beneficial microbes, beneficial fungi, they act to deter potential predators and pests, they act in the certain context of, like limonene is a great solvent against fungi because it exhibits phase toxicity against their cell walls, meaning that there's no chemical reaction that happens if you allow limonene to dissipate across the cell walls of a fungus. It literally doesn't have a chemical reaction. It will quite literally just melt the cell wall. That's called phase toxicity rather than chemical toxicity. And that's a pretty powerful thing when you don't need a chemical reaction, but you can produce a chemical that will, effectively melt something that's trying to come in and attack you and kill you. So,
jeez, man, that is wild.
Yeah.
Can you talk more about this relationship of microbes and terpenes? This kind of ongoing debate or conversation or whatever you want to talk about between what's largely grouped as organic soil growers and salt-based growers. Now, I believe there's probably way more to it than that, like we've talked about on this show, kind of like you said, the nuance of the situation. But it seems to me like that microbiological stimulation really contributes to a lot of these types of different expressions, different terpene profiles coming out. And, we focus on the NPK and things like that, but how much of it is just the salt-based nutrients often making life less hospitable for microbiology versus a living soil or a product like yours, which my understanding is it kind of feeds the microbiology? How does that all play into each other?
Well, so this is one of the things that I feel separates Rooted Leaf Agritech from some of the other, friendly competitors we have in the same shared space of carbon-based nutrients. I certainly don't want to, use this as an opportunity to, like cast my fellow competitors in a bad light. What I'm trying to do is maybe sort of make the distinction that
No, please.
what we're doing is fundamentally different, because if you look at how conventional and salt-based fertilizer programs work, they upset a thermodynamic equilibrium. Every time that you put salts on your plants, you're asking them to do work, and that requires energy. Where does the energy come from? You have to shine light on the plants. So this is why your EC, your ability to feed a high EC to the plants, is more or less directly connected to how intense is the light.
Right.
If you have plants that are nutrient deficient, one of the knee-jerk responses for growers may be to turn down the light intensity and allow the plants to kind of catch back up and create equilibrium. Another potential response might be to just up the EC. If you realize your plants are taking up more and more fertilizer in the presence of stronger and stronger light, you start to build this understanding like, hey, the ability of plants to process nutrients is actually driven by the power that comes in from the light. But that thermodynamic equilibrium continues to grow. It never, ever, it's impossible to reverse it, in the sense that the more salts that you feed your plants, the more energy you're asking them to spend. And eventually the energy taxation can be so great that you actually start to see deterioration of microbiological activity in the soil, because it's such a burden on them, it's such a tax, that it starts to wick away from the reduction power that they would otherwise afford towards more basic processes. And you see this more often perhaps with nitrogen than anything else. Nitrogen is a very interesting element. It makes up 1 to 2% of the plant's biomass, but up to 25% of the energy that the plants harvest from the sun can be funneled towards processing nitrogen in the form of nitrate into amino acids. It's a very, very, very large amount of energy that has to go into the system.
Right.
And it's, one of those things where if you're asking your plants to do the work there, you're quite literally preventing them from spending that reduction power on processing things like carbon and making compounds like monoterpenes and cannabinoids. Think about it this way, like when plants are exposed to the light, that light energy comes in, they convert light energy into a chemical currency that's called reduction power. That reduction power is just like dollars in your bank account. So if you work all day, you better have something to show for that work. You've got dollars in your bank account. Well, you have to go to the store and you have to feed yourself. You have to find something to buy. And imagine you have a tax that's placed on you to spend. You're forced to spend money on things that you may not necessarily want to, but you don't have a choice. This is effectively what's happening here. We're taking away from the total chemical currency, aka the reduction power that plants have, every time that we feed, chemical salts in excess. Whereas on the flip side, what we're doing here with Rooted Leaf Agritech is we're reversing that thermodynamic equilibrium by allowing the plants to access energy as opposed to spend energy. And this is kind of something that sets us apart, in the sense that when plants metabolize our chelates and our carbon-based nutrients, there's no energy expenditure. There's actually a net energy gain. So every time that they work, every day that they work, let's say they're making $500 worth of their, reduction power or their chemical currency. What we do is we come in and we multiply that substantially.
You give them
if you go to the grocery store and you only have $5 to $10 to spend on food, imagine if someone came in and said, hey, here's an extra $50 to $100, go ahead and buy whatever you want. Now, all of a sudden, the things that you couldn't afford to buy because you didn't have the reduction power become accessible to you. This is exactly the same way that plants are. And, more specifically looking at the way that some of these low molecular weight organic acids interact with things like nitrogen in the form of nitrates, we're putting specific flavors of carbon into the mix that actually allow the plants to chemically reduce nitrates with a much lower amount of energy spent overall. So we get an increase in nitrogen use efficiency. We get an increase in the conversion of nitrates that would otherwise require a ton of light energy and a ton of carbon substrate in the form of CO2 to actually make that building block to help buffer out the excess nitrate load that's coming up. We're doing that for the plants for free. We're saying, here you go. And we're watching them basically plug that into the right pathways. Those pathways start to grow. They become more and more highly expressed. And then the overall ability of the plants to sink nitrogen into their tissues goes up proportionate to how much of the specific flavor of carbon that we're feeding it. They are tied directly to each other, much like if your motor, going back to the car motor, if your car motor produces horsepower, that horsepower is hard linked to the tires that rotate based on the horsepower generation. And this is exactly the same way in plants. You may have these similarly different pathways that are all rotating, but they're connected like wheels are connected by an axle. There are internal processes within plants that help create an equilibrium such that the left tire spins proportionate to the right tire, and even further, that the engine isn't sending power to all kinds of random places like, oh, hey, whoops, my motor, accidentally misfired and it sent power to the wrong wheel. Oh no, what are we going to do about that? Plants aren't like that at all. Plants are extremely precise. They're extremely precise with energy coming in, energy being stored as a buffer compound, and then energy going out of the equation.
Let me ask you this. You talk about all these exchanges and, the taxation on the bank account, the amino acids to nitrogen, all that sort of thing, or rather the reverse. Is the currency adenosine triphosphate, this ATP, this universal energy molecule, or is it more complex than that?
ATP fits in. ATP is, accumulation of ATP basically represents the storage and the accumulation of energy in plants. The reduction power may be a slightly different flavor in the form of NADPH. Both of these are actually produced at the end of what's called the electron transport chain. So when the light comes in, the electrons get transported down this chain. It's pretty cool, very complex. There's hundreds of these, proteins that are all individually responsible and participate. But the idea is that they all pass energy back and forth to each other, and they kind of help create an equilibrium. Eventually, that electron transport chain ends with the production of NADPH, which is where you get your reduction power and then your free energy in the form of ATP. This is the basis. This is the starting point for what's called the Calvin-Benson cycle, or CO2 fixation or carbon reduction. So the ATP and the NADPH that are generated in the presence of light get passed on to Rubisco. Now Rubisco is powered. Rubisco has some energy going into it, and it's capable of doing something like sucking CO2 out of there, or, and maybe we shouldn't get into this today, but the oxygenation reaction of Rubisco is actually a beautiful and very, very proportionate thing. It's very balanced in nature. And I think Rubisco in C3 plants often gets a bad rep because it's something that has low specificity, meaning that it can act on CO2 or oxygen, and it has a slow turnover rate. But there's so many fascinating things about Rubisco that if you look at it in a slightly different light, you realize like, oh shit, nature optimized this. Nature has perfected over the past, 100 million years, the way that C3 plants run that oxygenation reaction, specifically as it pertains to generating reduction power to reduce nitrates without having to compete. This is sort of an enigma in plant biology, which is to say that when the electron transport chain is doing its thing, those electrons and the energy that's generated, plants are very, very aware, very much so aware of how that energy is going to get distributed and which kind of reactions are going to get run, because they're trying to maintain an equilibrium. They're trying to maintain a balance of all of these things going on all at once. And so the oxygenation portion of Rubisco is not an accident. It's not a misfire at all.
So it is much more complex.
Yeah, it's significantly more complex. And I would just challenge people, respectfully challenge people to consider, if Rubisco in C3 plants is so inefficient, and if it presents such a bottleneck, then why is it that over 95% of the plant species and all of the green biomass produced annually on this planet comes from C3 plants? Why are they so dominant across the planet for, at least the past 25 million years? And definitely they've been kind of perfecting their craft for the past 100 or so million years. C3 plants are remarkably well-tuned machines. They can actually take up more nitrates than other crops, and it's specifically because that oxygenation allows plants to generate reduction power to convert nitrates into their ammoniacal forms without necessarily competing for reduction power that might get funneled to CO2 and fed into the Calvin-Benson cycle. This is all such an intelligent framework and is beautifully balanced by plants.
Jesus, man.
The other thing that I kind of want to plant a seed, this is kind of our secret sauce here.
Please.
We haven't really talked to anyone about this quite yet. It's something that we're, processing internally, but the idea that Rubisco would just passively accept CO2 or passively accept O2 is not at all how it works. Much like your car has actual fuel pumps, and there's a specific hardware that your car has to introduce the fuel inside of where that fuel needs to go in order to actually get that proper combustion and to actually generate the energy. So plants are no different. Rubisco is one of the most important enzymes, if not the most important enzyme for plants. And so this idea that Rubisco would accidentally fire on CO2 versus O2, if you look at the thermodynamics of it, doesn't make sense. It does not add up. It actually violates what's called Michaelis-Menten kinetics, which is basically the study of enzymes and how they maintain equilibrium, and there's a whole sort of very complex topic to talk about there. But what we're realizing is that CO2 is actually fed to Rubisco. It's not passively. It's not like, oh, I'm going to grab CO2. Oops, I grabbed oxygen instead. Oh, well, now we have to deal with it. That's not at all how plants work. CO2 is fed to Rubisco, and the oxygenation reactions allow an equilibrium to be maintained because it both produces and consumes reductive and oxidative equivalents, and it maintains thermodynamic equilibriums in plants and otherwise very harsh and stressful conditions.
Man, we will have to follow up on this in the next episode because I told you, audience, that Nick is a wealth of knowledge. If you liked this episode, if you like how he's talking, if you want to support him or try out Rooted Leaf, go to rootedleaf.com. And again, Nick activated code GROWCAST just for you, 20% off. Really cool of him to do that. Like I said, Nick, I'd love to have you back on. This is already a return appearance, so I know you're down. But thank you, man, for dropping all this knowledge. I think you'll probably receive a pretty good feedback because this episode was very good, man. Thank you.
Yeah, you're welcome. I'm always willing and happy to talk about this stuff, with people. Part of it is I always want to tell people, don't take anything that I'm saying as 100% true. We're on the cutting edge of understanding all of this stuff about plant physiology. And with that comes the territory that is inherently high in risk of failure, meaning that there's a lot of stuff that we kind of postulate, we theorize, we hypothesize, we test it. We kind of refine our understanding over time. We kind of remove the ignorance, and we get to a spot where describing this is, more and more simple. Like I mentioned earlier, with carbon being 80 to 90% the weight of monoterpenes and cannabinoids, you don't have to have a PhD. You don't have to have an advanced degree to understand, it's mostly carbon by weight. So all of the cannabis growers that are, looking for high terpenes and high cannabinoids, they're really just farming carbon at the end of the day. Those molecules are mostly carbon by weight. So I hope it kind of, for those of you who have listened and taken a serious interest in this, I hope it kind of connects the dots and makes things actually easier to understand rather than adding more and more complex stuff that doesn't seem to make sense. All of this just comes down to balance, thermodynamic equilibriums. It's the transfer of energy and carbon coming into the system, being processed in the system, and then being exported out of the system in the form of terpenes and cannabinoids. And so I want people to understand above all that plants are just trying to maintain a very delicate, very nuanced balancing act. And that's the simple truth of the matter is it's all about maintaining balance. There are a lot of very, very complex things that happen, but that's all, kind of getting lost in the details, so to speak. If you take away nothing else from this podcast, just remember that plants are really based on very simple concepts, very simple laws, very simple aspects of thermodynamics, and they're doing a lot of complex work to help regulate what is otherwise just a state of balance.
Wow, man. Well, this was a stunning episode. We'll have you back again, rootedleaf.com. Instagram? Is there at Rooted Leaf Instagram?
Yep, The Rooted Leaf is our Instagram. Come check us out. If you guys have any questions, feel free to reach out. We'll answer, direct messages pretty quickly, and we love to chat about this stuff with everyone.
You rule, Nick. I'm sure you will see a nice boost there. Go and show them some love. And again, code GROWCAST live just for you guys. Thank you all so much. We are signing off here. This is Nick from Rooted Leaf and Jordan Rivers saying to all you growers out there, be safe and grow smarter. That's our show. Thank you so much to Nick from Rooted Leaf, and thank you for making that code GROWCAST for us at rootedleaf.com. So awesome of him. And we will definitely have Nick back on, I'm sure, GROWCAST TV and this main podcast. Before we wrap it up, though, gonna give love to AC Infinity. You know AC Infinity. ACinfinity.com. Find them on Amazon as well. Code GROWCAST15 is 15% off. Works infinitely on the website. Works once per account on Amazon. Grab the best tents in the game, the best inline fans in the game, the best booster fans in the game. Really great products. They've got a bunch of other stuff too. Just shop around ACinfinity.com, use code GROWCAST15, or grab one of their kits. It's bundled, it's discounted. It's a great bargain already, and code GROWCAST15 stacks on the kits. So if you've been looking to upgrade your space, now's the time. Go to ACinfinity.com and use code GROWCAST15, baby. Love AC Infinity. And thank you to AC Infinity for donating to Baby JJ's Journey. If you've been following me on Instagram, I've been posting for a charity project down here in Oklahoma that Jinx Proof turned me on to, and a great member, Mary Jack. And AC Infinity stepped up and helped out with that. So really, really cool of them. Thank you to AC Infinity. Thank you to all of you listeners. I appreciate you so much. Stay tuned for some badass content. I won't let you down. As always, GROWCAST will be here to help you. Go do amazing things in your garden. I'll catch you later.